This is the Analytical Chemistry course review specifically for titrations. You can stop this recording at any time to back up, review, or rewind and repeat any of the information that you're interested in. When we look at titration curves, we're talking about titrating, in this case, a strong acid and a strong base. So we're starting with a strong base because when you look at this graph of pH versus the volume added, at the very beginning, before we've added anything from the burette, we have a pH above 12. So this means that we're starting with a strong base in our beaker, a strong acid in our burette. As we start adding acid, and that volume at the bottom on the x-axis gets larger, you can see the pH stays fairly constant, and then you get a rapid drop down to a very low pH where we have excess of the strong acid. There's several things that you can see here. First, when we're titrating strong acids and strong bases, the titration curve and the equivalence point are very sharp, they're very distinct, and they're very easy to see. If you're graphing this, you can look for the point where the first derivative is at a maximum. So that's the maximum slope. You can also look for the inflection point where the second derivative is 0. But again, prior to anything being added, all we have in the beaker is strong base. As we start adding the strong acid, then drop by drop as the acid is added, it immediately reacts completely with the strong base, and you have some remaining portion of strong base left and water. And that's why we see very little change in the pH all the way up to the equivalence point. Exactly at the equivalence point, all of the strong acid has been reacted, all of the strong base has been reacted. By definition, that's where the equivalence point is, and because they're strong acids and strong bases, they react completely, and all that we have left at that point is water, and you see a neutral pH of 7. As we continue to add drop by drop the strong acid, then all we're doing at that point is adding strong acid to the water. So we can calculate the pH at each one of these points. Again, prior to the equivalence point, all we have is unreacted strong base and water. So we can look, you need to look first at how much hydroxide ion you started with, how much of it has been reacted with the acid, and how much is left. So you can look at the fraction of hydroxide ion that's remaining. So in this case, if you had started with 10 milliliters of hydroxide and you've reacted 7 of those milliliters, then you have, you've reacted 3 milliliters, then you have 7/10 of the original hydroxide remaining. You can calculate the pH of a strong base fairly accurately, but you do need to take into consideration that the concentration you started with is now diluted, because as you've added acid, you've increased the volume in that beaker and you've changed the initial volume, so you need to look at that dilution factor. From that you can get an OH minus concentration, and you can figure the pH from your OH minus. At the equivalence point, again, all of the strong base that you added has completely reacted with the strong acid that you've added. All you have is a water equilibrium. With the water equilibrium, we're looking at the Kw, and that has a pH of 7, equal amounts of hydrogen ion and hydroxide ion. At any point after the equivalence point, all we're doing now, again, is adding the strong acid to a beaker that has water in it. So we can figure out the pH of a strong acid solution. All we have to take into account at this point, though, is that, again, as I'm adding drop by drop the strong acid, it's being diluted by the water that was already in the beaker. So I can take my initial concentration of acid and multiply it by whatever dilution factor. So my volume of excess acid plus divided by my total volume is now going to give me my new hydrogen ion concentration, and I can figure the pH by the negative log of that hydrogen ion concentration. The situation changes slightly when you're not looking at both a strong acid and a strong base. So this example is a weak acid that's being titrated with a strong base, but we could be doing the opposite. It could be a weak base being titrated with a strong acid, in which case that curve would again be flipped. So what we're starting with is a weak acid in the beaker. We're adding drop by drop the strong base from the burette, and again we can see where we reach a maximum slope, and that is our equivalence point. As you get weaker and weaker acids and bases, the titration curves become more blurred, and it is much more difficult to be able to figure out where the inflection point is and where the equivalence point is. Again, sometimes that helps if you're using a spreadsheet, because you can look at the maximum slope of the line, or you can look for an inflection point where the second derivative is equal to 0. So let's think about what we have in our beaker. At any point prior to the equivalence point, we have weak acid that we've started with in the beaker. Drop by drop, we've added our strong base, and the strong base has immediately reacted completely. When it reacts, it gives us the conjugate base of that weak acid that we started with. And therefore, at that point, we have a buffer. So at any point prior to the equivalence point, we're in a buffer region. As we've added strong base and it reacted with the weak acid, it formed that conjugate base. So you can see from the titration reaction there in the middle that HA, which is our weak acid, plus OH minus, which is our strong base, gave us A minus, the conjugate base, and water. Remembering that any mixture of a weak acid and its conjugate base is a buffer solution. We can immediately go to the Henderson-Hasselbalch equation in order to figure pH. What you need to know at this point is how much relatively do you have of the weak acid and base. So looking at this table in the middle, our initial quantity, we started with whatever our initial amount of acid was, we'll call that 1. We have all of our initial acid. And we've added 3 milliliters of the base in this particular instance, where 10 milliliters is the equivalence point, is at the equivalence point. So we're 3/10 of the way to the equivalence point, and we're assuming starting with no conjugate base and no water. So when you look at the relative final quantities, we know that all of that strong acid reacted and went away, so there is no strong acid left. When it reacted with the weak acid, it left now 7/10 of the weak acid, because it reacted in a 1-to-1 mole ratio, and generated 3/10 of the conjugate base. So we know that quotient. And it's okay at this point to use relative amounts, the 7/10 and the 3/10, because we're going to plug into the Henderson-Hasselbalch equation. It is possible to do actual quantitative measures at this point by using the actual milliliters and the concentrations of each one that were added. But we can use relative amounts because we're going to plug it into that ratio. So at the bottom, pH equals the pKa plus the log of the base concentration over the acid concentration. So for this particular acid, the pKa is 6.27, and again we found out that our final quantities, we have 3/10 of base that have been generated, 7/10 of the initial acid remaining, and we can plug that ratio into the log there, and we get a pH of 5.9. We can do this any time prior to the equivalence point where we have a buffer. There is a specific case where we're at half of the equivalence point, where I've exactly added half of the strong base that I need to get to the equivalence point. So I've reacted exactly half of my weak acid. I've generated half of the conjugate base. So I have equal amounts now of conjugate acid, conjugate base. So when I plug that into the Henderson-Hasselbalch equation, I've got the log of 1/2 over 1/2, or the log of 1, and that goes to 0. So at that point, where I'm exactly half of my equivalence volume, my pH equals my pKa. And I can see that as another inflection point on the slope of my titration curve. At the equivalence point, again, all of my weak acid has been reacted. All of the strong base has been reacted. Both of those have now been converted to my weak base and water. So what I have at this point is a weak base equilibrium. And I go back into my weak base equilibrium equations that I know from chemical equilibrium. And I can look at the Kb and figure out the pH of that weak base, because that's all I have in my beaker at that equivalence point. You'll notice that this is not at a pH of 7. When we had the strong acid and strong base, all we had in the beaker at that point was water, and it was at a pH of 7. When in this case we actually have a weak base, and we're going to expect to have a pH greater than 7. So it's a weak base equilibrium in the beaker at that point. After the equivalence point, all we're doing is we're adding excess strong base to the weak base that was already in the beaker. We're making the assumption that the strong base is going to have a much, much larger effect on the pH than any of the weak base that was already there. So we're essentially discounting any contribution or any effect from that weak base. And so we're going to assume that the pH after the equivalence point is only due to the excess amount of strong base that's being added. We can look at the initial concentration of the strong base. We know that it's now diluted as we add it. So we look at the volume of excess base that's added over the total volume now, and we can get a concentration of OH minus. We can get the pH from that by remembering the KW equation. And so we can go from OH minus concentration to H plus concentration, plug that into the pH, and get a pH value. When we look at polyprotic acids and bases where there are more than one acidic or basic acidic proton, or it can accept more than one, and we look at those titration curves, they look very similar to the previous curves. You just see more than one inflection point. So what happens is that if we're titrating an acid, for example, it loses the first acidic proton completely, and then it loses the second. Or if it's a base, then it picks up a proton, it picks up the first one, and then it picks up the second one. So you see two buffer regions where you have a combination of the first conjugate acid conjugate base pair for the polyprotic, and then you have a second buffer region with the second conjugate acid second conjugate base pair. You have two inflection points that represent the two equivalence points. Again, depending on how strong or how weak the base is, those equivalence points become more blurred and more difficult to identify. Again, it's very important to kind of step back and consider what your problem is. What do you have in the beaker at any point? Do you have the first base or the second base, the first acid or the second acid? Has one been reacted completely? What do you have and what are you adding? And then you can figure the pH from that point. Again, you have your review booklet that does have several problems of this nature to give you some practice, and it has some more narrative descriptions.